I would just say they teach you.
Okay, guys. I'm sorry. We ready to get going for today? Okay. All right. So today we're going to be looking at we're going to be looking at regression models with autocorrelated errors. Okay. So the order of today's lecture is going to go with straight line regression with simple errors, so an AR1. We're going to talk about the definition. We're going to look at using Proc-ARIMA and SAS and looking at using Proc-AutoReg and SAS. Then we'll look at a real-world example, the Berkshire Hathaway data, and we'll compare some models. Then we'll take a break, and after the break, we'll come back and look at two more examples, Chipotle Mexican Grill and Lion King data. So that's what today looks like. Okay? All right. I'm going to do show. All right. This is what we want. Never know. Okay. So let me get myself situated a little bit better. Okay. So we're going to start the first half of the class talking about single predictor regression models with autocorrelated errors. And so the idea here, basic definition for a regression model with autocorrelated errors, we're going to consider a time series model where the current value of y is going to be modeled as a function of deterministic predictors while allowing for the errors to be autocorrelated. Okay. So what that means, I'll show this much. Okay. So what that means is that we're going to consider situations in which the error at one specific time is linearly related to the error at the previous time. The errors themselves follow a simple linear regression model. Maybe I needed to say that more clearly. So backing up one step. When we have YT, that's going to be predicted from a single predictor X, and the errors are, in this case, the simplest, going to follow an autoregressive process of order 1. That is, we're looking at YT equal to beta naught plus beta 1 xt plus e to the t, where these e to the t's are equal to rho times e to the t minus 1 plus nu to the t. This nu to the t are independently identically distributed normal with a mean of 0 and a variance sigma squared. So if we're going to, the errors themselves here are going to follow a simple linear regression model, specifically e to the t equaling rho times e to the t minus 1 plus nu to the t, where this is called, this rho is the autocorrelation parameter. Well, specifically, the nu term is a new error term that's going to follow the usual assumption of our errors being identically independently distributed, normal 0 sigma squared. So this model says that the error at time t is a function of the error at time t minus 1 plus some new sort of disturbance. Our model for the errors e to the t of the original y versus x regression is an autoregressive model for the errors. Specifically here, an AR1 in this case. One reason why the errors might have an autoregressive structure is that the y and x variables at time t may be, and most likely are, related to the y and x measurements at time t minus 1. And so here, Hill, Griffith, and Judge showed that the least squares estimates for beta 1 has the following properties. The expected, I said beta. So beta 1, least squares estimator is equal to beta 1. And the variance of the beta 1 least squares estimator is going to be equal to sigma squared divided by sum of squares xx times this formula. When the rho is equal to 0, this means that there's no correlation. What this simplifies to is that the variance of beta 1 is sigma squared E divided by the sum of squares xx. Okay? So using the least squares and ignoring autocorrelation when it exists will result in consistent estimates of beta 1, but incorrect estimates of the variance of beta hat 1, invalidating our confidence interval and hypothesis test. So using this idea of regression with autocorrelated errors, let's simulate some data in SAS and see what's happening with this kind of data. All right. So this is SAS code similar to what you've seen in the past. Possibly the differences come in from the previous slide, where here our E sub t's are going to be our autoregressive 1 errors. That's represented here with called it phi times e to t, the lag of e to the t plus epsilon, EPS. And then our regression, our outcome, yt's, are going to equal the regression model, right? So 0.02 is our true population parameter for the slope, 0.02 times time, our x variable, plus e to the t, the errors. Okay, so we have our regression, our y's created using regression, and we've created our errors using autoregressive 1. Okay. All right. So here, just to remind yourself, time is our independent variable, or our predictor. Okay. So if we examine this regression, we do a regression on this data in JUMP. This is what we see. We're able to see that the true value of the slope parameter, the estimate comes out to be 0.0187, etc. You think, oh, that's really close to the slope of 0.02 that we used to create the data, but if you check the lower and upper confidence intervals, you'll see that 0.02 does not even lie within this confidence interval range. If you take a look at the residuals after fitting the linear regression model, the residuals here, when you examine the autocorrelation function and the partial autocorrelation function, hopefully you would see that they are consistent with an autoregressive 1 model with a significant lag for the partial autocorrelation function at 1. So what we're going to do at this point is we're going to apply an autoregressive model of order 1 or a REMA model to the residuals. Okay, so an autoregressive model order 1 to those residuals. Okay. When you fit using JUMP, an autoregressive order 1 to the residuals, what do you see? You see here, there's a couple of things. You see that the coefficient is significant. Let me make sure you see that. It's pretty small. But the coefficient here is significant. It comes out to be 0.7 with a probability less than 0.001. And the residuals, if you look down here at the bottom, look to be white noise. All of the Liang-Zhang box Q statistics are not significant. So we would keep our null hypothesis. So these errors appear to be white noise. When we applied an AR1 to the residuals of our regression model. Okay, so here, don't get overwhelmed by the fancy-looking algebra. But basic idea. On slide 3, we saw that the variance of the beta hats are incorrect when using least squares if the autocorrelation exists. In other words, on average, the standard errors are often underestimated. So Cochrane and Orcutt created a transformation for us. This transformation, what it's going to do is adjust the linear model for serial correlation in the error terms into one with uncorrelated errors so that we can use the least squares for diagnostics. Specifically, they came up with, or specifically they determined that the transformation, so that we can still use our least squares context for y1, this new transformation is going to be equal to y1, and that yt for t from t2 to n, this is their transformation, is equal to yt minus rho times yt minus 1 times the square root of 1 minus rho squared. So this is a brief travel through the idea of how they created their transformation. You don't have to spend much time on that travel, but recognizing, you should know, the Coffer and Orcutt, that they're the gentlemen who came up with this idea of transforming our least squares estimates so that we can use the software and create programming. So because of these gentlemen, and I don't remember what the year was for them, because of the 1940s, in the late 1940s, because of them, we now have software systems to do this work for us, specifically in SAS. Okay, so in SAS, you can fit a regression model with correlated errors. So we're going to attempt to do that here with an autoregressive 1 error term. Okay, so you use Procurima. Using Procurima, the code, the syntax appears very, very similar to what you've seen in the past. The predictor variables that you are going to include, make sure you include them in the cross-correlation option in Identify. The idea for including them here is, looking up in SAS, when you want to include the effects of predictors, for example, past and current values of other series in the model, the correlations of the response series and the other series must be considered. And it makes it so that these series are then available for use as inputs in the model specified by this estimate statement. Okay, so if you're going to use predictors, make sure you include them in that cross-correlation option in the Identify statement. So when we apply this we use our Procurima with autocorrelated errors, specifically autoregressive errors of 1, order 1, to our data that we created previously. We're able to get lots of output. You'll get a cross-correlation option, provides correlations of your outcome and here the x. It provides a correlation between the outcome and your x variable. You can obviously see that they're correlated. But what we're interested in, typically, are estimates. Okay, so using SAS to fit a model with autoregressive 1 errors, we are able to get a better estimate of the slope parameter. Okay, it now falls inside the 95% confidence interval. Here is num1. This is you can see it here, the variable's time. This is our slope coefficient. Okay, this is our beta 1. When we simulated the data, our simulated data was simulated with a slope coefficient of 0.02. Okay, so it's significant, and 0.02 lies within the 95% confidence bounds if you just do plus or minus 2, plus or minus, I said that wrong, plus or minus 2 standard errors. You'll see that 0.02 from our simulated data does lie within the confidence bounds. So now, at the bottom, I have the estimates, reminding ourselves of what the estimate was using just straight linear regression, where it didn't estimate it accurately. Okay? So if we look at the residuals from SAS, went too far. Okay. The residuals appear to be white noise, as evidenced in the white noise probability plot. We should also check, because we want to use the idea for hypothesis testing, check the normality of your errors. And checking the normality of your errors, we're able to see that a linear regression, I'm on the wrong side. We're able to see that the residuals of the model appear to be normally distributed. Right? fairly good here, but if you're checking the QQ plot, looks very, very good. So the residuals appear to be normally distributed. So if we compare the regressions where we adjusted for the autocorrelation, specifically in AR1, to the regression where we ignored the autocorrelation, what you're able to see is that a linear regression here on the right that ignores the autocorrelation misses the movement, right? Misses the movement of the series. Forecast adjusting for the autocorrelation allow for much more improved forecasting. Right? So using the adjusting for the autocorrelated errors improves our ability to forecast. Just in a simple setup. Okay. So Procurema is not the only way in SAS to run a regression with correlated errors. You can also use ProcAutoReg. Okay. ProcAutoReg is an alternative to Procurema, and it's here at the bottom. Okay, so we have our same simulated data, and this time we're going to run ProcAutoReg. And so the in-lag option in the model statement specifies the autoregressive error process. So ProcAutoReg is when you have when you believe you have autoregressive errors. Okay, so it's specific to autoregressive errors. This, I'll talk about it later. But in ProcAutoReg, when you write, I won't write it. But for example, if I had an autoregressive errors 3 of order 3. I can also write, instead of a 3, I can write in parentheses 1, 2, 3. Okay, so there are different ways to write what order you're interested in. So you don't have to just write you don't have to write just a 3. You can also write 1, 2, 3 included in parentheses for in-lag. And that'll become important, you'll see later on, when we want to sometimes drop a parameter estimate. Okay. So comparing the two results from the Procurema with autocorrelated errors to the ProcAutoReg with autocorrelated errors, what we're able to see here is that the AICs and the SBCs match perfectly. The parameter estimates also correspond, and so the parameter estimates that we're interested in is the parameter estimate for phi for our autoregressive errors and for the beta 1, the coefficient for time. You'll see here, you might be concerned, we have our autoregressive errors 0.72 and the autoregressive, the phi for autoreg is negative 0.72. I don't know if you've ever encountered that in your past using another software system, but there are many software systems, and autoreg is one of them, that models moving averages and autoregressive models, specifically the equations, with negative signs in their formula. Instead of using addition, they're using subtraction. So that when they do the estimation of those parameters, they come out the opposite sign of what you might get from different software. So R works similar to Procurema in SAS. It works in the positive direction. The autoreg works in the negative direction. Okay, so typically when you're going to give or describe your model to your audience, most people think in the positive direction. So you might have to do some double checking if you're using a different software system to know which way what equation they're using in the background. Okay, so Procurema does it in the positive, ProcAutoReg does subtraction in their model. So you typically, most people think in the positive direction, so you're going to have to flip the signs of your time series errors. Okay. Everybody somewhat okay with where we're going? You might still be lost, but it's okay. It's okay if you're still lost. I'm okay with that. I have in a couple of slides a layout, a plan of action for what to do if you're trying to model your time series data with regression and it has autocorrelated errors. So it's okay if you're still kind of, where are we going? What are we doing? I have a plan of action. It's always crazy when you see it the first time. Okay, so we're going to take another look at the Berkshire Hathaway quarterly revenue data. This time, though, our goal is to fit a straight line regression model with ARMA errors. And so I've included a new data set in the data set folder because we want a predictor column, right? So it's a new data set. So at this point, Berkshire Hathaway, I believe, has like 3 different data sets listed there if you look at the data. All right, so what we're going to do, what we saw previously is that when we were looking at exponential smoothing of the Berkshire Hathaway, we found that an integrated moving average 1-1 model was valid. And this was previously. So now we're going to look at what is the straight line regression model with armor errors going to look like. And so, ta-da, the steps. We can take a pause. Okay, so if you're interested in developing a regression model with armor errors, what do? First thing you do is develop a valid regression model for y as a function of the predictors. Once you do that, what you need to do is then examine the residuals from that model, specifically examining the autocorrelation function and the partial autocorrelation function with the hope that maybe you'll be able to propose a model for the errors. Okay? If it's not clear from the autocorrelation and partial autocorrelation function what the model is of the errors, then move on and use an ARIMA model group to help you come up with model options for those errors. Once you've come up with proposals for the error term, you're going to use SAS and refit the regression model from 1 with those armor errors that you found in 2. Okay, so you're going to go to PROC-ARIMA, or if you just have your errors just look autoregressive, then you might go to PROC-AutoReg. Okay. Once you refit the regression model in SAS, using more than likely PROC-ARIMA, you're going to examine the fit from the model, including the residuals, in order to decide if it is valid, parsimonious model. Okay. Everybody's somewhat okay with the idea of what we're going to do. Fit a regression. From that regression, grab the residuals, look at them. See if you're able to determine a model for the errors with the ACF or PACF, not use a ARIMA model group, come up with some proposals, go into SAS and run those models with possibly different error proposals, and check out what the fit looks like on those models. Okay. All right, so looking at the Berkshire Hathaway data, quarterly data. First step is fit a regression model to the data. Okay, so I didn't like crystal clear say it, did I before? What was our X going to be? Did I say it on the previous slide? No, I didn't, so I didn't overskip. But what the X is in that data set is quarters since the beginning of 2000. Okay, so it's a variable that says the number of quarters since the beginning of 2000. And so fit the regression model and jump to that Berkshire Hathaway data. And what do you see? We have a significant predictor. You could also check out the R-squared adjusted is very large, but the reason for doing this regression was to specifically look at the residuals to see if we could come up with a proposal for the errors. Okay, so looking at the residuals, the autocorrelation function and the partial autocorrelation function, there seems to be this idea of a possible sort of damp sinusoidal in the autocorrelation function, and there's a significant lag at 1. Okay, so possibly I might look at an autoregressive 1. That's where we started from, so I hope you would think we'd go there again. So might look at an autoregressive 1, but if you don't trust yourself, which is perfectly legitimate, only being into time series, 2 months, take a look at the ARIMA model group. And when you look at the...
I have a question.
Yes.
The regression by itself, what is it telling us? That orders matter?
That order matters.
No,
If we look at
orders.
talking about the quarter since the beginning of 2000.
Yes.
So my issue or concern, I don't want you to take too much away from what the coefficient, the slope is telling you, because these estimators, the accuracy of them is is false because of the fact that we know that the errors are autocorrelated. Okay, so JMP or SAS, whichever one you use, will do anything you tell it to do. But you have to know one of the assumptions of linear regression is that our errors need to be uncorrelated. And that's violated here, right? So walking in, JMP or SAS will give you an answer. It'll tell you what the slope is, and it'll tell you whether it's significant or not. But is it a reliable test? No, because we violated the assumptions before we ever walked in. So I don't want you to take too much away from what this coefficient tells you, because it's false. It's false. Okay. All right. What was I saying? Oh, we were looking at what possibly we could use to model the errors. And so I think I say my idea possibly is an autoregressive one, but to double check yourself, use an ARIMA model group, right? Help you. Okay. ARIMA model group here. I did an ARIMA model group for autoregressive orders from 0 to 2 and moving average orders from 0 to 2. Okay. And what it shows me is that the autocorrelation, partial autocorrelation suggests, as we saw in the previous slide, the idea that we're looking at an AR1 model for the residuals. The ARIMA model group finds that an AR1 model for the residuals is best in terms of SBC. So this is that was my inkling, that was our inkling, and it was backed up by the ARIMA model group code run. Okay, so we're going to move forward with the autoregressive 1 errors. Okay. We can still take another. Is there a question?
1 second, let me turn you up.
Okay, so I think I've had the question before, and I've run away. So, long story short, when it comes to the intercept, if you do not have a difference, did I say that properly? If you do have a difference of order 2, say seasonal, non-seasonal, you have a difference of order 2, do not include an intercept. If you're looking at 0, or you're looking at difference of 1 or a difference of 0, you should look at both, with the ultimate goal being, if you're trying to use it for forecasting or prediction, you go with the model with the best AIC, right? So when you're exploring, trying to discover what model to use, you need to use both, the idea. If you're doing this ARIMA model group, I look at models with and without an intercept in your final decision-making goal. And so that's my answer. Okay, all righty. And so here, simplicity's sake, I know what it looks like. And so I went with no intercept because I knew the outcome before going in. But if I was a new person walking in, I never looked at this data before, then I would have checked both. I would have used no intercept and used an intercept. You have to do it both ways. I hope that answered your question. Okay. I think I heard a yes. Okay. All right. I think we're here. All right. So the goal now is we're going to model the regression residuals as an AR1, and those resulting residuals here you can see. So this is our second step where we fit the autoregressive, we fit the regression to the model, and then using SAS to refit the straight line regression model with the AR1. Oh, I said that wrong. The resulting residuals appear to be white noise. The Q statistics are all not significant. Okay. And so now, mean of 0, constant variance. So we're now we'll be happy with autoregressive 1 errors. We're going to refit the straight line regression model using SAS. I said that wrong. We're going to fit the regression model with autoregressive 1 errors. using SAS. Okay, so here, that's the Procurema using the autoregressive order 1 errors, p equal 1, to our Berkshire Hathaway data. A question in the back, Sarah.
So on the previous slide, the residuals that we're looking at there,
just
is that from the AR1 to make
So
sure?
this is fitting an AR1 to just the residuals. So the residual variable, if I said that properly.
So in the right-hand corner,
These are after fitting an AR1
okay,
to the residuals.
so it's the residuals of the
It's residuals of the residuals. That's the confusion of this lecture, is we are often at the very end of our steps looking at the residuals of the residuals, right? And we're hoping that those residuals of the residuals look like white noise. That's going to give us the validity for our model. So just to verify for those who are distanced, Sarah's question was, what is this picture? This is a picture of the residuals after fitting an AR1 model to the residuals from the regression. All right. So now, because it looked like white noise, we feel comfortable, let's move forward and use SAS to actually fit straight line regression with AR1 errors to our Berkshire Hathaway data. Okay. When you fit this straight line regression with AR1 errors to the Berkshire Hathaway data, this is what the output looks like. Okay, so we're finally at the final step, if things look good. Here, we're going to examine the fit of the model, including the residuals, in order to decide if it is a valid parsimonious model. So the parameter estimates of phi and beta 1 are significant. Okay, you can see both of those here. Quarter since beginning, that's our beta 1. This is our phi. Looking at the residuals appear to be white noise. You can see that in the white noise probability plot. And the residuals are close to normality, with the exception of deviations in the tails. Some deviations in the tails. Okay, so fairly normal, close enough. If we want to look at comparing, the straight line regression model that we just performed with our beginning straight line regression model that we did in JUMP, what do we see? We just eyeballing it, you see that the estimates of the slope coefficient are somewhat close, 7.64, 7.54, but as we showed previously that they're somewhat close, but as I said, ordinary least squares numbers are not good estimates of the standard errors specifically, and so they're often these standard, well, because let me double check, let me say something again. You see the standard error for the straight line regression is 18.76. You see the standard error for the beta 1 from this straight line regression model with AR1 errors as 33.36. Your mind says, oh, this standard error is better, straight line regression. Let's go use that one. It's better standard error, smaller. But that's the issue. Ordinary least squares numbers are not good estimates, specifically of the standard errors. They're often deceptively small. So this idea for using straight line regression models when your errors are autocorrelated, it's going to falsely indicate that this model is superior. Okay, so you have to be aware. You have to look at the correlations. Yes? It's okay. How do you check for the autocorrelated errors? So first off, you would look at, I think off the top of my head, back in the regression course, I looked at Durbin-Watson as one thing you could look at. If you were clean, didn't know anything about the data. But if you look at your data and if you looked at your time series model, just the Y variable here, because you're supposed to visualize your data before you move forward with any kind of modeling. When you visualize the data, I hope you would see that there is obviously some correlation in the data. That should be pretty evident just in a typical time series model that's not white noise. You're going to see some type of pattern going on, right? So it's already going to lead you that there's some correlation going on in this data by itself, which is going to then lead to this idea of you're going to show up in the residuals, no matter how you model it. Okay, but Durbin-Watson is one way. It's a quick statistic you can perform to see if there's autocorrelation in the residuals specifically. I don't know off the top of my head what the syntax is for Durbin-Watson in SAS or in JUMP. I didn't have it, but I know it's there. It's the probably most popular. I think it's I do believe, an option in like a linear model, PROC-REG and SAS. It's a built-in option. Okay. Maybe during the break, I'll just pull it up and give you the code, the syntax for Durbin-Watson tests.
But if you have a variable that's time, then it's safe to assume that.
Yes, that they're but if you were you didn't say you weren't paying attention. You just move forward. I'm going to model, this Y with this X, and you didn't visualize it, you didn't look at it. Once you then saw the errors from the regression, so you just applied regression to it, you can see that when you're typically, you can see some autocorrelation just in the residual plot, right? That when you're negative, you kind of stay negative for a while. When you're positive, you kind of stay positive for a while. That might just easily show up in the residuals if you do a straight regression. Okay? So that's without any test, without anything, just looking at it. You can see that, hey, we're kind of hanging out below the middle line. We're hanging out above. When we go up, we stay up. When we go down, we stay down for a while. So that's the kind of thing that would kind of show. I think one of my, which one? What's my next data set? Not the Lion King, Chipotle. Chipotle, when we get to Chipotle, I think you can see it when we do the regression. I'll show you where it looks like you can just see the autocorrelation before you ever move past the regression. Okay. All right. Okay, so once again, using straight line regression when you have autocorrelation in your errors, you're going to get some false estimators. And that's for the wise data analytics person to recognize. For the unwise data analytics person, they're going to possibly, sadly, run with this when it's falsely leading you to the idea. And we saw that with the image of the straight line regression in the data. It wasn't grabbing any of the activity. It just gave us a flat measurement versus the regression with the autocorrelated errors gave us a much better forecast. So last time when we were looking at the exponential smoothing, we ended up with an integrated moving average 1, 1. And so let's take a look and sort of explore this a little bit further with that whole idea of standard errors. So if we assume that the true model is yt equal to beta naught plus beta 1t plus e to the t, okay? If we take the difference of that data, of that model, and so we end up, well, that's a typo. That's supposed to be t minus 1. That's a typo. So that's supposed to be t minus 1 here, okay? So yt minus 1 is equal to beta 1 times t minus beta 1 times t minus 1 plus et minus 1 simplifies to beta 1 plus et minus 1. So this beta 1, when we do this differencing, is estimated by the mu in this output. Okay, this beta 1 is estimated by the mu in this output. So what you see here is that using straight line regression model with AR1 errors, the estimate of beta 1 is here, 764, and the estimate for beta 1 from the integrated moving average 1, 1 is 808 approximately. The standard error for that one is 141.8, standard error is 33.4. Okay, so estimates of the beta 1, as you see, are fairly similar. The standard error, or the estimate based on differencing, is much, much larger than using straight line regression with AR1 errors. Okay, so let's further compare these models using SAS. Because you still, just because bigger standard error doesn't mean, let's take a look. We want to see the forecasting, right? So the first part of this is our regression with AR1 errors. The second procurema here is our integrated moving average, 1, 1. Okay. So if you visually look at the forecast for the two models, the one with the regression model with AR1 errors, the integrated moving average 1, 1, you see here that the forecasts look fairly similar to the naked eye. Okay, they look very, very similar. we delve a little deeper than just looking at the forecast, what you'll see is that integrated moving average 1-1 does have a lower AIC and SBC than our straight line regression model with AR1 errors. The AIC here, 1270 compared to 1290, 1274 for SBC compared to 1297. Looking at the forecast for one time ahead, specifically 2017 quarter 2, the actual forecast was 57,518. Our regression with AR1 errors forecasted 61,799, and our forecast for the integrated moving average estimated 62,248. Okay. So appears, if you're just straight looking at the estimate, but both of the confidence intervals include the actual value. If you were just looking at the forecast, you might be feeling, oh, the regression model with AR1 errors has a more accurate prediction. But in actuality, if you look at the comparison of their residuals, they kind of go back and forth with the idea, if you remember, that the AIC is leading us to the better model with regards to prediction, happens to be at this point the integrated moving average model. Okay? Keep going.
How do you produce that table in SAS? What I do is I take it to JUMP.
This is JUMP.
This
This is JUMP. Okay, so moving further, comparing them still some more. You can see here that this is the forecast for the integrated moving average model on the x-axis, and these are the forecasts with the regression model with AR1 errors on the y-axis. The forecasts correspond fairly well. The residuals don't necessarily correspond as well as the forecasting, but you can see it more clearly what's going on. But what I wanted you to specifically take a look at was a box plot for the residuals for the two models. And what you can see, this is the straight line regression with the AR1 errors in blue, and this is the integrated moving average model 1-1 with in red. And so what I want you to see here is that the residuals appear to be a little more symmetric with regards to the regression model with the AR1 errors as compared to the integrated moving average model. And one of our assumptions to move forward in the world of this regression is that our errors are normally distributed. So it does meet that requirement to some extent when you're looking at the residuals from the regression model. Okay. So just something to note, and something I'll point out again in a moment when we look at another model. So here, I'm going to move forward with the regression, the straight line regression model with autoregressive errors of order 1. I'm going to move forward with this idea of the blue model. Examining outliers. We still, luckily, since we're in SAS, we're able to see and determine if there are any outliers. When you run the code to determine whether or not you have outliers, what you're able to locate 3 possible outliers when you use the significance of 0.005 with a maximum of 5. Okay. Once we've located these 3 outliers, we then want to, as always, include them into our model. That's what I did here, allowing for these 3 additive outliers. Okay. And take a look at what happens when we include these 3 additive outliers into the model. Okay. What you can see here is that all of the parameters are significant. Okay, so we have our autoregressive parameter estimate, we have our slope coefficient, we have our outliers. They're all significant. If you move over here, we're able to take a look at the residuals. The residuals appear to look like white noise. Also, you could say, look, the normality looks okay, except for at the ends, at the tails, and it's very, very small, but this is -2 and +2. If you run it again to look for any other outliers, what you'll see, you're able to locate one more outlier. Another outlier was detected. So include that outlier in the model. So now we're looking at a total in this code of 4 outliers included in the model. And the output for including all 4 outliers in the model, checking to see if there's another outlier. Luckily, it comes out to be 0. So we're going to stop here with the 4 additive outliers included. All of the parameter estimates are significant. Okay. And the residuals appear to be white noise. Okay. And normality appears to be acceptable. So let's take a look at the forecast for this model. This is a linear regression. This is a straight line regression model with autoregressive 1 errors, allowing for 4 outliers. Okay, so now we're going to take a look at the forecast. So now the forecast for 1 step ahead is 57,015. Previously, back on slide 28, it was 61,799. So the forecast has much improved, allowing for these 4 outliers, where the truth is 57,518. Okay, so allowing for outliers here has improved the forecast question.
So isn't this forecast giving us forecasting the residuals of the regression, or is it actual?
It's the actual y. Okay. The question was, is this model forecasting the residuals or forecasting the actual y? So what Cochrane and Orcutt have done in SAS is sort of translated the idea of our ordinary least squares estimates that we use in regression. They've transformed them in such a way that it now can accommodate the idea of autocorrelated errors. Okay, so, all right. And so we've improved our forecast. Revisiting what we looked at, I'm sorry. I thought I just looked at this. Let me go to the top. Yeah. Okay, so allowing for the 4 additive outliers. Maybe I just, do I have?
The other model.
Thank you. I was like, do I have duplicate sides? Oh, this is for the integrated moving average. Thank you. Okay, so this is for the integrated moving average, allowing for 4 additive outliers. Yes, the same 4 additive outliers. What we end up here with is the forecast is 59,159. Previously, for this integrated moving average, it was 62,248. That was also talked about back on slide 28. When the actual is 57,518. So similarly, including the additive outliers, this integrated moving average model has improved when you allowed for those outliers. When we compare the 2 models, including the forecast from the models allowing for these additive outliers, the one with autoregressive 1 errors compared to the integrated moving average model. So the forecasts, as they did before, correspond fairly well. You see here, the residuals have sort of similarly correspond in a better fashion. When we look at the normality of the errors, now that we've added the outliers, that integrated moving average model now looks slightly more symmetric than it did before. Okay, so before it was less skewed, and now it's gotten closer. It's not perfect, but it's gotten closer to symmetry after you've allowed for the outliers.
The AIC was still better for the,
Integrated moving average. Did I?
we showed it.
I'm
with
trying to
2
see.
different slides. So
I'm trying to see, did I include them on here? Yeah, so I can compare them for you. So the integrated moving average model allowing for the additive outliers had a AIC of 1240, and the AIC for the straight line regression model with AR1 errors had an AIC of 1258, some decimals, what, 1258 for the straight line and 1240 for the integrated moving average. Okay. So at this point, most of us, if we're deciding between the 2 models, you make your own choice, but possibly go with the integrated moving average, but make your own choice. Sometimes it's easier to explain regressions to outside audiences. And if you definitely want to include predictors, that's the way you'd want to go. So I think that's the last slide for this part. Okay, so that's let me show this again. I showed lots of them. So that is the first walk through this world of regression models with autocorrelated errors. So what we've examined and looked at is a straight line regression with AR1 errors, sort of the simulated fashion and in the world of the Berkshire Hathaway revenue data. So we're going to take a little break, and after that break, we're going to then examine the idea, what we looked at previously. We only had one predictor. We only had one X variable to input into the regression model. That's not always the case. We fancier models. So we're going to look at multiple predictors into our regression models and how to go about coming up with an accurate model, a valid and parsimonious model. We're going to do that through looking at two data sets. The first is Chipotle Mexican Grill data, and then we'll look at some data from Broadway show Lion King. Question from?
Are we going to interpret the parameters?
Yes, we're going to interpret the parameters when we get to the Chipotle Mexican Grill more clearly. Okay, so please take a break. It's about 6:55 on this clock. I'm a little hungry. I'm going to run and grab a bite to eat, so maybe 7:10, okay? So I can go back. And if I'm saying his name right, Genty is not here right now. But I'll reiterate it when he returns. Back to this. Where are my other slides? I want this to go away. Here we are. Genty, a classmate sitting here, asked right before the break, well, what about interpretation? I said, oh, we'll get to it when we move into the next set of data to Chipotle, but let me just go back. The interpretations of the slope coefficients have not changed from your regression course, okay? So in this data set, we didn't do any transformations, and so literally the interpretation of our slope coefficient is exactly the same from regression. So 1 unit increase in X, here quarters since the beginning of 2000 will lead to an increase in the Y of about 739, that kind of idea. So the interpretation of the slope coefficients have not changed from your regression course. Okay? All right, so I'll reiterate that when Genty joins us in a moment. All right, let's move it on. Okay, so you can see where we are. I don't have too many windows open. So you can see where we are. So where we were, we learned about a straight line regression with AR1 errors and examined Berkshire Hathaway data. Now we're going to move on to a little fancier of a regression model where we have multiple predictors, and we're going to look at Chipotle Mexican Grill and examine the ideas of what model to use, and we'll also look at some data from a Broadway play called The Lion King. Okay, so that's where we're going today. Okay, so I think that's big enough. Let me get to where we are. Okay, so similar to what we just did with the idea of straight line regression with autoregressive 1 errors, or the Berkshire Hathaway examination, and we found a straight line model. We're going to now look at time series model. We're going to look at consider time series models where the current value of Y is now going to be modeled as a function of multiple deterministic predictors while allowing for the errors to be autocorrelated. In this process, we're going to look at the quarterly revenue for Chipotle Mexican Grill. The goal here is, our hope is to develop a time series model for the quarterly revenue of Chipotle Mexican Grill in order to provide forecasts of that quarterly revenue for quarter 3 of 2017. We're going to develop 2 models. When looking at this data set, we're going to develop a time series model, one that you would have developed before you walked in here today. And then the second model we're going to look at is a regression model with time series errors. And we're going to use the following predictors in that regression model. We're going to use total number of existing Chipotle stores at the beginning of each quarter, and the number of new Chipotle stores opened during each quarter. Okay. You can find the data in the data folder. So we're using two predictors. Chipotle is interesting because things to remember, if you remember about Chipotle in the past, they've had some major issues. They've started encountering outbreaks that sicken their customers. So this started in 2015, and in 2015 there were a total of 5 grouped outbreaks. E. coli was located at a Chipotle in Seattle in July of that year, 2015. Norovirus was located in August in Simi Valley of 2015, and Salmonella was located in Minnesota between August and September of that year. And then beginning in October, E. coli was located in many, many states at Chipotle's, and Norovirus was located in December in Boston. So the history of Chipotle and their outbreaks are going to play a factor, let's hope, and hope we can see them in our time series model and our regression model, hopefully with autocorrelated errors. Okay. So here, to start the process of looking at the data, if you look at the data, looking at the regression model, using the two predictors, existing stores and new stores, to predict quarterly revenue, what we're able to see, we use new stores, existing stores, what we're able to see is that there appears to be non-constant variance in the residuals. Okay. So with this non-constant variance in the residuals, we're going to look at a logarithmic transformation of both the revenue and the predictors. So when you look at the residuals, or when you look at the, let's look at the leverage plot or the actual by predicted plots for these regressions, and specifically down here, this residual by predicted plot, what you're able to see is the idea that there's evidence of outliers in the residuals. When you look at, I don't know if you remember leverage plots from regression. The idea behind a leverage plot is along the x-axis, maybe it's easier to talk about the y-axis. Along the y-axis, we're looking at the residuals, if I'm saying this right, the residuals of y regressed on all the other predictors. Okay, so here for this leverage plot with existing stores at start of quarter, this is the residuals of y regressed with new store openings, right? That's on the y-axis, and then on the x-axis is the predictor regressed on the other predictors, right? The residuals from those two plots. And so what you see with leverage plots, if you remember from your regression course, is the slope of the line that's created should be equal to the slope coefficient. Okay, so it's telling you the relationship that's sort of remaining between the actual predictor you're looking at and the outcome. And so what these leverage plots show, they show what you see in the regression output to some extent, is here you see that existing stores with revenue, the slope of the line appears to be positive, etc. And you see when you look at its estimate, it appears to be 1.24, which is going to correspond to that slope. When you look at the leverage plot for new store openings versus revenue, what you end up seeing is that it's fairly close to 0. And if you look at the estimate, we end up with a negative 0.01. It also looks a little negative. So we're able to see the relationships between our predictors and our outcome with these leverage plots. The conclusions I draw after looking and examining all these things, what I'm taking away from here is that there does appear to be evidence of some outliers in the residuals. There also appears to be some autocorrelation in the residuals. And Jinty's got again. That was his, I think his question about, how can you see if there's maybe some autocorrelation going on? in your residuals, but the idea here is as you move sort of left to right, what you're seeing is this idea that as we go up, we kind of stay up and we stay positive for a while. And then when we come down, we stay negative for a while. When we come up, we stay up for a while with a couple of downs. So this idea of, I'm not going to call it a pattern, but the idea that what's happening when it goes positive, it stays positive, and when it goes negative, it stays positive for a moment. That idea is evidence of the idea that there might be some autocorrelation in the resistance. And I didn't take the time to look up Durbin-Watson.
But this is still constant enough to be a valid model for the regression.
Yes, I would say yes. Oh, yes. And double checking that we did do, I should have done a side-by-side plot of the previous. So the data was much more spread out in that megaphone shape than what you see here with these log transform variables. I think I've said everything I wanted to say there. Okay. Maybe not. Okay, so once we've performed our first step, where we've done the regression of the predictors on the outcome and determined that this is where we're moving forward with, we want to take a look at the residuals of that model. When looking at the residuals of the model, the goal is to examine the autocorrelation function and the partial autocorrelation function with the hope that we can propose a model for the errors. That's not always possible. And when it's not possible, then I would move into the world of an ARIMA model group to help us determine what models to propose for those errors. And even when it is possible, you might want to use the ARIMA model group to just give yourself some to assure yourself of where you might be going with those errors. Okay. Looking here, are we able to propose a model for the errors? Even at my own, at this point, I would say, so this would be a proposal, right? That maybe we're dealing with some damp sinusoidal here, and that might say, oh, I don't know, right? You want to go towards this idea of, I might jump out at AR5, but that would just be a guess. So with this autocorrelation function and partial autocorrelation function, I would be open to examining the ARIMA model group to give myself a better idea of where to go. Okay, so if you do a ARIMA model group in JUMP, and I did it here, what I examined and what came out is the model with that we probably should consider first with, it has the smallest AIC, is a moving average 2. Okay, so looking at a moving average 2 model, smallest AIC value. I use and apply a moving average 2 fit to my residuals in JUMP. What I'm looking for is verification that the residuals, that the residuals look like white noise. When you see here, all the Q statistics are non-significant. So yes, the residuals do appear to be white noise when I fit a moving average 2 to the residuals from that regression. The parameter estimates are significant. Okay. And so now I feel more comfortable using SAS to actually fit this regression model with moving average 2 model. Okay, so this was not an idea. The moving average 2 was not one that I just saw in the autocorrelation, partial autocorrelation function. Okay, it was provided to me as an idea from the ARIMA model group run. Okay. All right, so applying a moving average 2 to the errors in SAS. See, make sure in your cross correlation you put your predictors that you're using. Tell it in the estimate statement what errors, what's the model you're going to propose for your errors. Okay. And so when we apply when we apply using SAS, a regression model with the two predictors and modeling the errors with a moving average too, what we're able to see is that both of the coefficients, the beta coefficients are significant. You can see them here. Both of the beta coefficients are significant, log existing stores, log of new store openings. And the moving average parameters are also significant. Using SAS, we're always examining and moving to check to see if there are any outliers that are detected, and it detected 2 additive outliers and 1 level shift. Okay. But before we move into allowing for those additive outliers and that level shift, take a look at the residuals. Right. Okay. You can see that the residuals of the regression model do appear to be white noise, with a mean that appears to be fairly close to 0 and constant variance. So things were looking pretty good. We need to include those outliers. Okay, and level shift. So when we, I'm sorry, before we get there, I'm still wanting to get to the full model, do a comparison, okay? So a comparison from the original regression model, where we were examining what model to put with the errors, to this model where we've now fit an MA2 to the errors. Let's look at the differences, right? So let's compare them. So what you see here is that the regression model, this was our original, regression model with identically independently distributed errors does not find the coefficient for log of new store openings to be significant. And as we see the log of new store openings in our regression model with MA2 errors, we are able to see that log of new store openings is significant. Right. So now, actually fitting those additive outliers and that level shift to our data set, the 2 additive outliers and the level shift, and rerunning the model, also checking for further outliers. Something to note, as a lot of times as these models get more and more complicated, the default in SAS, I believe it's the default, is the conditional least squares as the method of estimation of the parameters. Majority of the time in the semester that we've been doing maximum likelihood estimation, the ML. We've been doing a method of ML for estimating our parameter estimates. And so the idea behind conditional least squares is, in all actuality, maximizing the log likelihood is sometimes very, very complicated. And so this uses more of an iterative process. The responses that you get when you use conditional least squares are approximately equivalent to what you get with maximum likelihood, but software typically has an easier time running conditional least squares than maximum likelihood. So if you run into, I always would start with maximum likelihood. It has the distributional assumptions behind it, but if it bogs down and doesn't run for you, then go on and use the default, okay? So in this conditional, there's no assumption on the random error terms. Okay, so this was us fitting. Our goal was to allow for those additive outliers and level shift, that 1 level shift. So when we add the 2 outliers and the level shift, what we see here is that the errors do not appear to be white noise, and so we're ending up with a not valid model. So we need to now go and examine or investigate a different model for our errors. Okay, so the number 1 model with AIC that ARIMA model group told us to go to gives us, once we add in the outliers and the level shift, it tells the residuals don't appear to be white noise. Okay. So we go back to the drawing board is what we do. So going back to the drawing board, let's rerun in SAS. Question?
Erica.
Is it written? Oh, yeah, I'm waiting, Erica. What is that? No, that's a different person. Why did we use 0? So you could use So the question from Erica is, why did we use 0 to 7 for the P&Q ARIMA model group originally back when we did the search? When I was looking at the autocorrelation and partial autocorrelation function, I didn't have any clear-cut plan of action of what I thought the errors looked like. I thought maybe there might have been an AR5 going on in there, but not sure. So you just want enough, not to kill your computer, to have it running forever, but you do want to do some exploration. So 0 to 7 was just to get me out there far enough to do some exploration at that point.
Piggybacking on that question,
Mhm.
there was no differencing in the range that you looked at, so why didn't you look at differencing?
Because I didn't see any crystal clear need for differencing. Did you see?
Well, because you couldn't see anything clearly, I just
Oh,
thought I was
so
throwing a one.
So I'm not against 100%. So there wasn't any obvious increase in trend, but so as an exploratory idea, you can include a 1. Hopefully next week when we start learning about a procedure in SAS, we will still do some of this, but some of it will be done for us a little bit. But so this is exploratory on our own individual basis. So how much and what you investigate is completely dependent upon your time that you have to spend. You'll rank it in order of AIC or SBC depending on which one's more important to you, and you'll move from there. She's okay with that. So here we're now going back to the drawing board of this is step 3. I think I'm bad with the steps. I think it's where we're rerunning our model in SAS, trying a different proposal. So this is, I don't quote me on that. I think it's 3 or 4. It's 3. So we're rerunning 3, step 3. Now using autoregressive 5 errors. Okay. Okay. All right. So when we run in SAS a regression model with AR5 errors, this is what our output looks like. And what you'll see here is this in SAS? Yes, this is in SAS. That all of our parameter estimates are significant, except for the AR3 parameter estimate. You'll see here that it has a p-value of 0.85. Okay, so before we move on, let's take a look at the residuals. And you'll also note that when we ran that, it did locate 4 outliers. Okay. But let's take a look at the residuals before we move further. Sorry to pause in the middle of the slide. When you look at the residuals using an autoregressive 5 for the errors, what you're able to see here is that the errors do appear to be white noise with a mean of 0 and a constant variance, thank goodness, versus before they didn't look so good. Okay, so back to the idea here, comparing our parameter estimates, comparing our output from the regression model using an AR5 for our errors compared to the regression model with identically independently distributed errors. What we're able to see is that the predictor parameter estimates are all the predictors are all significant here. Log of existing stores and log of new store openings. And so still the same issue, log of new store openings, not significant in the identically independently distributed errors model. Okay. So I noted, or I pointed out, that the AR3 parameter estimate was not significant. So we're going to run a model that it's called a gap model for the errors. And this is our first time ever doing it. Okay, so here, typically when we've encountered the world where we have run a model on a time series and we've come up with a non-significant parameter, and we were looking at maybe an AR3 and the second one was non-significant, we moved on. We said it's not parsimonious enough, and there are others that are, so we'd move on. But that's not always what you have to do. You're the one trying to model your data. So that's not a requirement. There is a way to make it parsimonious in a way where all of the parameters are significant, but it's all about how you are going to interpret it for your audience, right? And so here, this is called an AR gap model, and I call it an AR gap model because what we end up doing when we go to model those errors, that third term for the autoregressive parameters was not significant. So moving forward, I'm going to use regression to model this data, and I'm going to use autocorrelated errors, specifically in AR5, but recognizing that I'm going to not include the third parameter estimate. And so I mentioned previously that it was in the Proc Autoreg slide that whenever you can include in your syntax the idea if you're interested in an autoregressive 5, you could put a 5 there for the P. P equals 5. But you can also specify you like P 1, 2, 3, 4, 5, and it understands, SAS understands that you're doing an AR5. So in that same idea, you can write 1, 2, 4, 5 to let it know that you do not want to model the third parameter in an autoregressive 5. Okay, so everybody understand the point of this slide or to talk about is here the P in the estimate term. That SAS understands I want to do an autoregressive 5, you can put a 5 there. But if in that 5, out of those 5 parameters, you don't want one of them estimated, then you can list out the ones you do want estimated. Okay? This same syntax applies in the world of that Proc Autoreg when you're talking about its autoregressive parameter for your lags. Okay, all right. And so, all right. What we're looking at here is looking at now the parameter estimates for the regression model with AR gap model errors, and it's allowing for the 2 level shifts and 2 additive outliers. Okay. That we saw previously. Let me make sure. Yes. Okay, so when we ran the autoregressive 5 with all of the parameters included, it located 4 outliers, 2 additive and 2 level shifts. So we included those here and did not include that third autoregressive parameter estimate because it was not significant. And what we're able to see, we're going to be able to now talk about this model, and the idea that's probably of most of importance to people is interpreting, right, the slope coefficients. So we're going to interpret this idea of log of existing stores and the slope coefficient for log of new stores. We're going to do both of them. All right. So it's just revisiting and remembering what you learned in your regression course. Okay. All right. Just making sure you get that information. So what you learned in your regression course, the formula, it's kind of here, is you learn the idea that to talk about a 1% increase in your X variable, it needs to equal, when we log transformed both the predictors and the response, the interpretation for a 1% increase. We move for a 1 unit increase to 1% increase because of the whole idea of moving from the traditional numbers to a log transform. So we move from actual numbers to percentages changes. So a 1% increase in existing stores. The Chipotle's quarterly revenue is predicted to increase by 100 times 1.01 raised to the beta coefficient minus 1. And that comes out to be a 1.25% increase. For a 1% increase in the 1% increase in existing scores, the revenue for Chipotle should go up by 1.25%. That's what this model is stating. And then for a 1% increase in new stores, Chipotle's revenue should increase by just 0.03%. So new stores are not at this point making that much of an impact, as you see, on the revenue. Yes.
So on the
Question.
previous slide, on the white noise, we're just kind of going with that, right?
Yeah.
I
I'm
mean,
ignoring it. Yes, I mean, at the moment, just because I wanted to talk about the log transform variables, et cetera, but I don't see your name, Sarah? Sarah pointed out, and I did gloss over it, the idea that when we were looking, we didn't look at, I didn't talk about, but the residuals are displayed here for this model of autoregressive 5 errors, removing the third term, including all of the outliers and additive shifts. The white noise probability for this model is rejected, right? The errors do not look like white noise. So you could wiggle around it, but it's, so to be, if you're trying to be 100% valid, I'd say it's not a valid model, but we'll move forward with it, okay, investigating it a little bit further. Okay, so just that was a reminder about the interpretations of log transformed relationships between predictors and outcomes, okay, from your previous regression course. And so here on this slide, looking at the forecast using this model, looking at the forecast, the predicted revenue for 2017 quarter 3 is equal to the exponentiation of this forecast, which comes out to be $1,296 million, $1 million. Okay, $1,296 million. It's just horrible the way it says that. And so I did a quick look. I didn't delve deep. I was kind of rushed today, I'm sorry. And so I didn't look at their quarterly reports. I just did a quick Google search. And so don't quote me on this 2017 quarter 3 revenues, but I believe it's a little less than that. It's the actual, I believe might be more like 1,100, oh, a little more, I said a little more than that. A little less, $1,130 million. And just in my little quick Google search, I didn't look at their quarterly returns. They blamed their quarterly 3 returns at being less than what anyone predicted on not necessarily their outbreaks and things, but on hurricanes. There were a lot of hurricanes in 2017, if you remember, here and elsewhere. Okay, so they blame their low revenue on the hurricanes. All right, so that was the idea of the forecast. This is a visual of the forecast for 2017 quarter 3. Okay, all right. So that's the one possible model using regression with here autocorrelated autoregressive 5 errors, gap errors. Let's take a look at Chipotle Mexican Grill in a way that you might have looked at it previously, right? Before you ever walked in here today, what would you have done? Given Chipotle's quarterly revenue, you would have created a time series plot of that revenue. And what you would see is that it appears the revenue increases over time, but as you move in time to the right, the variability also increases. So we need to, one thing, first stabilize the variance. So one way to stabilize the variance is to do a log transformation of the revenue. When you do a log transformation of the revenue, the time series plot appears in this fashion. Okay? And so this is the log transformed revenue time series plot. And so yes, the revenue, the variability has now calmed down some, but what you still see, what you saw in the previous slide, what you can still see is definitely an increasing trend. So with that increasing trend, as we've seen in the past, recommendation of doing a difference of that data. Okay. So when you difference the log transform data, the time series plot is displayed in this fashion. Okay, and when you examine, if you want it, examined the autocorrelation function, the partial autocorrelation function of this difference log transform data, I have to say it's not perfectly clear to me what the autocorrelation and the partial autocorrelation functions are guiding me to, but it does appear to be some seasonality in the data. And one idea that this is quarterly data, so one idea for the seasonality is a definite idea of the quarters. So you might investigate using 4 cycle periods in a year. Okay, so when the autocorrelation function and partial autocorrelation function do not guide you to a strong sense of what the data should be modeled as, it's always great to take a look at what's at your disposal, the ARIMA model group. Okay, so here for the ARIMA model group, I take a look at, and here I look at autoregressive non-seasonal orders from 0 to 2 for autoregressive and moving average. Always remembering that we did first differencing. And then for the seasonal, I went with 0 to 2 for both the moving average and the autoregressive, and with the possibility of differencing it in the seasonal trend with 4 observations per period. So here we go. When you examine the results from the model comparison, what we're able to see here is that the seasonal ARIMA 0111004 produces the lowest value of SBC, and then the 0110014 produces the second lowest value for SBC. Okay, so those are the 2 models I'm going to move forward with and try to examine what they look like. So looking at our first one, seasonal 0111004. So if you're trying to remember what does all that mean, the first part is our non-seasonal model components. The second part is the seasonal model components. And so in the non-seasonal model components, we have a difference, and we have a moving average of order 1. In the seasonal, we have a autoregressive of order 1 with the cycles being 4. Okay. And so when you fit an ARIMA 0111004 to your data, what you're able to see is that it does appear to be a valid model. If you look at the Lejeune box Q statistics, all of the p-values are greater than 0.05, telling us that it looks like the residuals from this model appear to be white noise. If you then go back and look at your parameter estimates for the components of the seasonal and non-seasonal components of your model, they are also both significant. So, valid model with the outliers looking like white noise. The residuals looking like white noise, but there also are some outliers. Please note those, a few outliers. So we're going to then, once we've come up with an idea for the time series model, let's take a look at it in SAS to see if we can locate any possible outliers. So applying the time series model to the log of the revenue difference data. Here, remember we're doing for here, this time series model that we're investigating has a non-seasonal moving average component of 1, that's a Q equal to 1, and a seasonal component of autoregressive 1 with cycles of 4. So it's this multiple, so this is a 1, but it's our multiples, our cycles of 4. Okay. It's been a moment since we did that lecture on seasonal ARIMA models. Trying to remind you of what the SAS code looks like. Okay, so when you apply that model to the Chipotle Mexican Grill data, what we're able to see here is that the residuals appear to be white noise, and when it examined the outliers, it located 4 total, 3 level shifts and 1 additive outlier. The parameter estimates, as we saw, are significant. So moving forward with a model that includes those outliers, this is the code for that. This is just our traditional SARIMA model. That's what we're doing. So don't be lost and confused. It's just a SARIMA model. what we're able to see here is after allowing for the one outlier and 3 level shifts, the residuals appear to be white noise. Okay, so we're excited. If you double check the parameter estimates, they are all significant. Alrighty. And then if we look at the forecast, or the predictions, right? The predicted value for 2017 quarter 3 is equal to, oh, that's a typo. That's a typo. Oh, no, I'm sorry. Yeah, it is a typo. Is equal to exponentiation of 7.11. I need to correct that, I'm sorry. So that's the idea of the forecast. I have to plug that in. Similarly, ignore the result at the end. It's close, but that's the previous one. I just copied and pasted. And so this is a visual of the forecast using the model, the SARIMA model with the 3 level shifts and the 1 additive outlier. So that's what our model looks like when you use time series. So depending on what you're interested in, makes your decision on whether or not you're going to go with a traditional time series model or if you're going to use regression with the hope of incorporating predictors. That idea of incorporating predictors at times can take a lot of exploration. Okay, you're going to have to probably explore quite a lot of models for your errors to verify that in the end they appear to be white noise. Okay, so it's going to take sometimes a lot of work to explore all the possibilities. Okay, alrighty. So moving on. Or do we take a break? Moving on, because it's not much. 20 slides. So the next set of data that we're going to take a look at is about the Lion King performance on Broadway. Really interesting scenario in the world of time series. Important things to know about Broadway shows. The idea behind Broadway shows is only 1 in 10 make money, and typically 2 out of 10 lose all their money. Okay, so that's a big deal in the world of Broadway. And this show, The Lion King, down here, debuted in 1997, July, in Minneapolis, and was an instant success. And then soon after, in October, it appeared on Broadway at the New Amsterdam Theater. That's when it opened, and officially opened in November. But it was an instant success from the moment it opened in Minneapolis and then was able to then move to Broadway. After a while at the New Amsterdam Theater in 2006, it moved to the Minskoff Theater. And to make way, the Mary Poppins Broadway production is what started being at the New Amsterdam Theater. And so it's still at the Minskoff Theater in New York, and it's been running for more than 6,700 performances. It's Broadway's, at this moment, 4th longest running show in history, and the highest grossing Broadway production of all time. It's having grossed more than $1 billion. So, important stuff about The Lion King. What happened in New York, sort of an idea, is there was Bruce Springsteen, and he came out with the Bruce Springsteen's Broadway show, and it raked in $2.33 million in 1 week from just 5 performances. Okay, most Broadway shows do 8 performances a week. Okay, so the Bruce Springsteen show did $2.33 million in just 5 performances. You want to compare that? The only shows that week that brought in more money than Springsteen was Hamilton, that brought in $2.93 million, but mind you, it's 8 performances, and Hello Dolly brought in $2.35 in 8 performances. Okay, so only 2 shows did better, but mind you, they had many more performances. The average ticket price at a Springsteen show was $497, which is extremely high when the regular average price for a show in Broadway is $129. People always say Hamilton tickets are super expensive, so the Hamilton average price is $272. So Springsteen is, almost doubling what most people consider an expensive show. Okay. Okay, so the average price was $4 something, or I already forgot the amount, $497. Many of the tickets for Bruce Springsteen were sold for $850 each. Okay, so that's like crazy expensive. The idea, how he was able to ask so much, people love Bruce Springsteen, but the idea was they were getting an intimate show, an intimate night with him, because the theater where he was performing only had 939 seats, when a traditional rock concert has thousands and thousands of seats. So people were willing to pay such exorbitant prices for this intimate encounter with Bruce Springsteen. So the ending of his week, that first week on Broadway, the week ending October 8th was a strong one for Broadway in general, and people attributed that to the Columbus Day weekend and the start of the previews at several fall shows. The 29 productions running that week in October grossed $30 million, which was up from $23 million the week before. And that $23 million was a total of 24 shows. Yes?
Can we do a time series?
So the question, I think someone needed a levity break. The question was, can we do a time series for the Mega Millions draw tonight? I wish. If I could, I wouldn't be here probably. Okay. Yeah, I wish. And so back to Bruce Springsteen. We're almost done, guys. So the ending here is the overall grosses for that week ending October 8th were up 20% over the last season, and attendance was up 6%. Okay, so thinking and knowing all of that was going on in Broadway with the idea of the Lion King performances, and now this week in October for Bruce Springsteen, let's take a look at the data set. Okay, so our idea here is we're going to look at the weekly revenue per performance for the Lion King on Broadway. Our hope is to develop two models for gross per performance using weekly data from the beginning of 2009 until the end of August 2017. A regression model with predictors is going to be performed. That's going to include week of the year, and hopefully ARMA errors. And we'll also take a look at applying a time series model to this weekly revenue per performance for the Lion King. Okay. So this is an image of the data, the gross per performance from 2009 to August 2017. Okay. So first step, when you're trying to create a regression model with ARMA errors, take a look at the regression model. Okay, so here we fit the regression model for the using the two predictors, which are week of the year and I said that right? Three predictors: week of the year, and performances. And as you can see, these three predictors are nominal variables. Okay, so when you look at the effects test for nominal variables, it's looking at the effect for all of the parameters, the number of the parameters associated with that effect. So to truly then look at each of the factors, you have to do the expanded estimates. Okay, and so what you're able to see here is that the effects for each of these predictors, week of the year, and performance, using this regression appear to be all significant. Okay, all seem to be playing a role. I don't know how much you remember from your regression class with nominal variables. So when you look at the effects test, what are you looking at when it says NPARM? We're talking number of parameters that are associated with the effect. And when you're dealing with nominal variables, this number here is one less than the levels you have, right? Okay. So for year, we have from 2009, as you know, to 2017. For week of the performance, we're talking 1 through 53. And then for performances, then performance numbers go from 5 to 9, with 8 being the traditional, the typical. Okay. So we can visually, it's easier to, looking at this entire expanded estimates is like, well, what is it saying? What does it look like? It's easier if you visually display your expanded estimates. So the next slide shows the expanded estimates for each variable, or for each effect visually displayed. And it's just a graphical display of the estimates from the previous slide. And you can see here, just looking at the estimates, that as this is the year variable, that as we go move in time, it appears that the gross, right, becomes positive as we move in time. When you look at the number of performances, not so crystal clear of any obvious pattern. When you look at the weeks of the year, it does, they seem to group in groups, right? Some low grossing and then others high grossing. Okay. So let's look at the regression model with predictors including week of the year, year, and performance. These are the residuals from that regression model. And as you can see, the residuals do not look like white noise, right? So since they do not look like white noise, we should take a look at the autocorrelation function and partial autocorrelation function with the idea of trying to come up with a model to propose for the errors. Okay, so we're looking at the autocorrelation function, partial autocorrelation function for those errors from that regression model. And does anything jump out at you? A couple of things jumped out at me. And so what I looked at and saw was the idea of maybe the possibility of a moving average 1 in the non-seasonal part, and then here, and a possibility of maybe a seasonal part. You see a significant lag at 7. 14 is really close to being significant. It's right on the line. So there might be a cycle of 7. It's just my idea. So on this model for the Lion King, I went and examined possibility of some suggested models. I didn't do an ARIMA model group, okay, but in your own time you could go and explore that. I did not do an ARIMA model group. I just moved forward with the idea of some possibilities, okay? And so here, the idea here is possibly a period of 7, a P of 7 for the seasonality part, and a Q equal to 1. Similarly, and all kind of combinations of that. So a P equal to 1 for the non-seasonal part, and a Q equal to 7. Idea for the seasonal part, really a 1 with the seasonality of 7. And so these are the possible suggested models that I was going to investigate. I did investigate all of them, these 4 models. Okay. And so here's the, I skipped my code. I'm skipping the page. Here is the, I don't know where I put that slide. Here's the SAS code for running the analysis here of a seasonal P of 1 with the lag, with the cycle of 7, and a non-seasonal Q equal to 1 for the errors, with a lead out of 7. That's what I'm going to look forward to. Things I wanted to note, so we can talk about it. When you're doing your cross-correlation, your comparison group, if I'm correct, when you're doing your cross-correlation function, leave out, if you're thinking about, we have to label all of our effects, leave out your comparison group. Okay, so everybody okay? So here, Comparison group for performances was 8, because that's the typical number of performances for year 2009 and for week 1. All right, so this is an examination of the output from the regression of all 4 of these proposed models for the errors. And when you look at the proposed model for the errors, the goal is to get a valid model. When you look at this output, only 2 of them show us valid models. The regression model with seasonal P equal to 7 and Q equal to 1 has residuals that are white noise. Seasonal with Q equal to 1 and 7 also appears to have residuals that are white noise. But if you look at the SBCs and similarly, I think even the AICs, comparing these 2 models, the P of 7, seasonal 7 and Q equal to 1 has the lowest value for SBC and AIC out of those that have valid residuals. Okay. So I'm going to move forward with this model on your own. You could have done an ARIMA model group and explored all the different possibilities. So moving forward with this model, what you're able to see here is in bigger, is that definitely the errors appear to be valid, that they do look like white noise. This is just the blown up image. And then taking a delve into looking at the parameter estimates. What you can see here is that we saw previously that the errors do appear to be valid for this model, and that the parameter estimates for the predictors are significant. All right, say that properly. Parsimonious. Oh, I said that wrong. The significant in terms of the errors. That's what we're looking for. So you want the parameter estimates for the errors to be significant. Every predictor doesn't have to be significant. And so here we go. They are the MA1 and the AR1 with the seasonality of 7. They're both significant. So we end up here with a valid and parsimonious model in terms of the errors, which is our ultimate goal. We want our model to be valid with regards and parsimonious with regards to the errors. Okay, so looking at the forecast, this is an image of the forecast with the predictors of year, week of year, year, and performances for our model that was selected. This is a visual display of that. And then, show here. Okay, these are the forecasts that were displayed in the visual previously, and also looking at the residuals. One of our assumptions we would like for the residuals to appear to be normal. When we're using a regression model with autocorrelated errors, we would like our resulting residuals to be normal, mean of 0, and they appear to be fairly, the box plot, similarly the histogram, appear to be fairly symmetric. If you look at the mean/median, because it is fairly symmetric, they're going to be equal, close to equal, close to 0. Okay. And then the last image that I have here is of the actuals and the forecast. So the red is the actual values, and the blue is the forecast. And so this mark here is the idea of the actual and in the forecast. This was when the Bruce Springsteen week, first week occurred, and so the model definitely doesn't grab it all the way for the Lion King, but it doesn't make it 100%, but it does, you know, it tries to follow. So in general, I believe this model is a fairly good representation for the gross performance weekly revenue for the Lion King. So you can see, it was still able, everyone made a lot of money with that Columbus Day weekend. Kind of blew everything out. And this is just the residuals from this model on the left. Are there any questions? So it's fairly accurate forecast for gross performance for the Lion King. Okay, like silence. All right. So that is the idea of using regression with autocorrelated errors and how to get SAS/JUMP/SAS to help us get there to creating a model that would fit the data. And so where I'd like us to go in the future is I did place a breakout session / a homework assignment on Blackboard, and the idea is to try to do a regression model with predictors and autocorrelated errors for a data set from Wicked. From Wicked. That's what that homework / breakout session is about. I'm momentarily a little overwhelmed with grading. So I put that assignment due for 2 weeks from today, just to give myself a little leeway on grading. That's not a limitation to you turning it in. You know, typically for the homework assignments or breakout sessions, it's just a 1 week turnaround. So if you live by that, great, turn it in. The turn-in is there, but I am giving you a little wiggle room because I probably won't be able to look at it until 2 weeks out. Question from Andrew.
On eCampus, it was listed for the 5th, which is a Monday. I just wanted to confirm.
Oh no, it's Tuesday. That's just I sent Javier. That's me, and I hadn't had any food before I came, so that was me sending him the wrong date. So he'll adjust it to the 6th. It's 2 weeks. It's 2 weeks out. So I was off by a day, correct? Okay, so that will be adjusted to the 6th. It's actually 2 weeks from today for the due date. And then I also wanted to say something about projects. I know some people emailed me because they weren't able, I believe, to submit more than one document or more than one file, I believe is what the issue was. And so I did receive a couple of emails from groups who were submitting more than one document. So I got those, and we'll go from there. My goal is to look at them within the next few days. And so you'll be able to move on with your group if you'd like. I might hold off another week before moving forward, but if you've already gotten your data, it's perfectly fine to move forward, but things might even get easier after next week's lecture. So just, if you haven't done it, it's okay to wait 1 more week to do that. Are there any questions? Not yet, not till you try to do the assignment. So feel free at this moment to break out into your groups if you want. I'm flexible. I'll be here, but if you like to work at home with your group, that's perfectly fine. Or you can move to breakout sessions. I'm sorry, Mason, I didn't prompt you to that. Is that okay?
I mean, it's fine, I can set them up, it'll take me a few minutes.
So if you want, Mason will set up your breakouts. I'm sorry, Mason, that's my mind today, I'm sorry. He will set up a room for you if you're interested in staying and doing the breakout session, or you have 2 weeks to accomplish it with your group. So you work at your own pace, whichever way you want to do it. So confer with your group and make your decision, and let Mason know which way you want to go.
I'll just set them up.
You'll set them up?
And then if you log on, I'll add you to it, and y'all can go from there.
Okay, all right. So have a nice evening with your group, or moving on to home, whichever way your group decides. I'll be here.
You can if you want.
The room is better. Yeah. Just take out into the hall.
I only have 3.
It'll be just me or-
I can't imagine. 5:30 barely gets to do it.
Sorry.
So imagine. One gets everything, and then there's go busy.
Oh, okay, yeah. But some question, each one you want to try to show. I'll do whatever for you though.
We can leave for a little.
Yeah, both,
Your wine's ready?
People are like, oh my God. Oh God. Yeah, no, and nobody's like, oh, we didn't know. They see a man. Oh my God, what's happening? And don't even see her. Look at you, you're such a good thing. Isn't that the way you look? Yeah, oh my God, I'm seeing her.
I'm sorry?
think we're good.
I can go either way.
Most of us like dig in there and look at it.
I knew it after.
Before you can,
My mind.
yeah, it's hard to infer what you really.
Is there any special thing you do last time?
That's how you said.
Is it important? Why? Is it expensive?
Or it's usually
Really? Went to Mexico? I know it's because the soil is more sweeter than federal. So, you know, imagine Alaska, I mean, I guess you get the basic apple. Oh, yeah. What's the cheapest thing? Relative to Texas? Is cost of living there higher? Just because the convenience.
Yeah, and I guess. I call it, what do we call it? The isolation tax is what we refer to. Small population.
What think you about driving?
Yeah?
Unless I kick me out. I don't know how far is the nearest city. Is that the closest big city?
That's the closest. I mean, really.
Metropolitan too, right? Juneau and Fairbanks?
Well, yeah, Juneau too, that's even more expensive. Fairbanks is like considered the and then Juneau.
So Anchorage is the biggest. Fairbanks second. So Juneau's the capital.
Juneau's the capital. It wouldn't exist.
Fairtown has a bridge.
Yeah, right. And that's a joke too. Yeah, that bridge too. While we were up there, while oil prices were high, they started buying up all the gardens.
Never
It
materialized.
just, it goes, it's like interest.
I think it's like even too much power. I think it's just slow. Yeah, so I was being like, I was looking for candidates for voting. I mean, some of it is some of it okay. But it's just a symbol by capture. It's just like easy to understand.
Just, the sad thing is then, you know,
A lot of reliance on one item. Alaska is where there's. What else is there? Ice?
oil and military, that's where it comes from.
Oh, yeah, yeah. Russia defense line?
Yeah, yeah, I mean, pretty much.
You think these people hiding in the rocket, just like know what I mean?
Yeah.
Yeah, the self-reliant. They have in Texas too. Texas, if you've been to West Texas, there's nothing. Literally just like, my friend did that when Y2K hit. He was so afraid. He thinks this the planes will fall. No, we're just laughing. We cash out silver. But we did get there for like 2 weeks. He's a reporter now. He was on a big one. He's always prepared. We're just laughing. Because where's Tim? Oh, you didn't hear him? He's gone. He'll be back like, when the world annihilation happened.
He's in a funk.
Yeah, that's exactly what he did.
Yeah,
So I can only imagine Alaska is even more distant. There's gotta be areas that's like nobody probably even been there for 100 years.
yeah. Or you step here, it's like, I'm the first person who's ever
Yeah.
stepped on this spot. Yeah, it's crazy. Good to see you, man.
Friday's my last day.
Like last Friday.
I was like 5 minutes ago. You missed me to do one. They're paying me. Well, no, I found out later in charges. I have stopped investing this week, so it's not a lot. It's like 2,000 shares. Our stock is it's like worth it. I was like, hey, yeah, that's worth it. Yeah, I know. You should stay in the league, right? Yeah.
It's a lot of it. And you have a job. Just look over what the comments I said and see if you see where you're supposed to go. Oh yeah, and what department? Oh, this after school program? After school or summer? The summer one, I've seen it, but I haven't. Gotcha, yeah. Yeah, what was the age range in your group?
Range from 6 to all.
I've always been thinking about putting my kids in some of the summer programs.
Yeah.
But I can't do it.
I know.
Yeah.
So the thing that most people find crazy about is the
Oh.
but the
Gotcha, so have you heard of the
No.
franchise Ninja?
Yes, I have.
Yeah, so I just went to a party at Code Ninja with my 6-year-old, which is, they start at 7, but I believe this group started at 7. Okay, so this one, she told us you have a chance to get a little bit more official. But it was her spiel was really, I was interested. I don't have the funds to pay for it with my 3 kids and their other activities. But it was really, if I did, I thought that would be a nice story. It sounded fabulous for kids.
It is. Lots of stuff. So they can learn about self problems. They just
The motivation, yes, going here, they love rewards. So the idea that they would get a belt and keep moving, that would motivate them to do it.
How to build Mario games.
Mario.
So basically, build their own character based on what they want. They import the library.
And so you taught them that in the summer, in one summer? Like, an older kid could have walked away with knowing that. What was the strategy